So friction comes in two types. There's static, also known as starting friction, and there's kinetic, also known as sliding friction. You have to break static friction to get something to start sliding. And when you break static friction, sliding friction takes over. Yeah.
Yeah, we did.
Right, we did? All right.
That's where we stopped though. Like you wrote the symbol and then we stopped.
All right. Did the whole thing to show you what it looks like.
Yeah, a little bit.
They draw the little lines and got on a tangent or something yesterday. So static friction is an inequality. And kinetic friction isn't. Static friction can start at 0 and build up to some maximum. We know it is proportional to the normal force, in the same way that the kinetic friction is proportional to the normal force. And I did say there's a symbol we use here. The symbol we use is the Greek letter mu, which looks something like that. Now, again, whenever we have a new letter, I tend to like to give you context for how it should look, so that when you draw it on your test or in homework, I know what you mean, and so will your test grader. So it should look like this. It's a lowercase letter and follows the general rules of a lowercase letter. So if you have a P or a U, it's like that. Okay, so it's like a U with a little bit of flair. Typed though, like in Times New Roman, it's kind of got a squared off side like that, but it should be about half the height of a regular letter, but the front of it should hang down. Does that make sense? You guys got that? Okay. So for the coefficient of static friction, I'll put a little S here, and for kinetic, we'll put a little K here. In general, the coefficient for static friction is more than the coefficient for kinetic friction for the same material. So generally, your maximum static friction will be more than the kinetic friction. So if you've ever had experience pushing stuff around, you know that it takes a little more force to get something to start sliding, but once it is sliding, it takes less force to keep it going. And that's generally because the maximum static friction generally is greater than kinetic friction. Now, static friction is an inequality, because I want to remind you that if you start pushing on an object, it won't necessarily start moving. In order to get something to start moving, you have to break static friction. But once it's sliding, kinetic friction immediately takes over. So these problems are always going to be problems in which the net force on the object is oftentimes 0. Now, I don't want to say always, often. Because the object is staying in place. But so we handled a couple of questions where the net force isn't 0 and reminded us that the issue here is that the object doesn't move with respect to the surface. In this one, it does move with respect to the surface. All right? So here's the problem I want you to do. And I think we can do this one together. Consider you get a job at Publix. Yay. Working person with income. Then I go in there and you say, "Hi, Mr. Shelton." And I'm like, "Yeah, nice to see you." Put my stuff in the bags. And your boss tells you, "Hey, kid, go move that box across the floor. I want you to slide it from here to here." And you say, "Yes, sir, you're the boss." So you walk up to the box and you push on it. Okay? there is a coefficient of static friction of 0.4 between the box and the ground. How much force do you have to apply to get the box to start moving? That's the question. How much force do you have to apply to get the box to start moving? Now, obviously this question is a force question because it's asking about force. So you got clear clues as to what this problem is asking you to do. And we're not talking about you, we're talking about the box, right? How much force do we have to apply to the box? So start by doing your obvious things. Draw a free body diagram. I'm skipping a step, but it's on purpose. I want to come back to the whole, is it a first law problem or a second law problem, okay? So, let's go ahead and draw a free body diagram. Give me an arrow that I should draw here. Excellent, the weight. We'll draw an arrow straight down. Call it the weight. What's another arrow I have to draw? Normal, it's a good one too. Nice and easy, it's on a surface, so I have to draw an upwards arrow, and I'm gonna make that arrow the same size as the weight, because I think those have to be balanced. Give me another arrow I need to draw. Friction, all right, so what direction should I draw friction? Left, all right, excellent, excellent, excellent. So refreshing to have a class that talks. And anything else? You, that's right, you're pushing on the box. What direction should I draw that? There we go. Now, here's where we have to get into the weeds a bit. What force are we overcoming? Friction. And is it the static frictional force we're overcoming or the kinetic frictional force? Static. So, in dealing with the static frictional force, we're dealing with a situation in which the object is staying in contact with the surface. We want to find out how much force we have to apply. What this is going to tell us isn't that. It's going to tell us how much force will keep the box in place. So obviously, we'll have to apply more than whatever we get for our answer, right? This is going to tell us how much force will keep the box in place. Now, I know applying no force will keep the box in place. And I bet that as I start to apply a force, friction will start to build. It's a responding force, right? So at the end of the day, what we're going to end this problem with is an inequality. Something that's going to tell me all the forces I could apply that won't get the box to move. Does that make sense? All right. Now I'm going to assume that you guys haven't worked with inequalities in this way. And I think that's a good assumption to make. That way, even if you have, you'll get a good refresher. So I'm going to call the force you apply applied force and this static force, or static friction. And let's start by saying this must be a net force equals 0 problem because the box is not moving with respect to the surface. All right, so I see an obvious coordinate system already in place there. So can I just call this the positive x direction and this the positive y direction and go with that? So I'll break this up into the net force in the x direction equals 0. Net force in the y direction equals 0. And this is the part where you guys can speed run it, right? You know things. So I'm thinking applied force minus frictional force equals 0. Is that good for you guys? Any question about it? Excellent. Then we're going to go say normal force minus weight equals 0. That look good too? All right. All right, that's it, right? That gets us all the way down to we've applied Newton's laws. There's a few things we can do here at the end that we know about, right? For example, let me just kind of take all of this and kind of focus us on just these pieces for a minute. We know things, like we know that there's a way to calculate weight that has to do with mass, correct? How do we calculate weight? Right, so we could do a little bit of math and realize this equals mg, right? But that's really about it. We could say that the applied force equals the frictional force. We could do that too. But I think we are at the end of our problem when it comes to what Newton's laws can do. We've done all the substitutions that we know about. We're left with these three things. And this is at step 4. We have to analyze the problem and try and figure out an answer. My experience is that most of the time you guys don't know what to do with inequalities, so I want to help you. I like to call this preserving the inequality. I want to preserve it so that in the end of the day, when I get something that I can use, it has an inequality in it. So it's helpful to know that in order to preserve the inequality, we can't substitute out of this equation. Like we can't say that the frictional force equals mu times the normal force because they're not equal, right? They're by definition unequal. So we substitute into this equation, meaning I'm going to take and substitute into this equation. I want this value. I want the applied force. But I want to do so by substituting into something that has an inequality. So I'm going to make those substitutions to keep an equation with an inequality. All right, you guys learned how to work with inequalities. I don't think you learned how to substitute with inequalities. So we will substitute into an inequality. And that means the applied force, this is the answer, this is what I'm looking for. How hard do I have to push? Will be less than or equal to the coefficient times m times g. Do you see what I've done here? I've substituted into my inequality. And what I've produced is an inequality. This tells me that all of these forces between, because this is an inequality, between 0 and whatever the maximum is, none of those will work. So as long as I apply a force that is less than or equal to 0.4 times 50 times 10, which how much is that? 200. So as long as I apply a force that is less than or equal to 200 newtons, the box will not move. Do you see what this inequality is telling us? It's not telling us the answer. It's telling us every force that won't work. So how much do I have to push with? Yeah, anything more than 200 will do. If I push with more than 200, the box moves. But I can get right up to 200 and it won't move. This is how you deal with static friction. Static friction gives you a range of values. Everything from 0 up to a maximum. So when you're dealing with static friction, you set the net force in such a way as to understand that it's either going to be 0 or ma, but there's a limiting factor, and you will substitute into this limiting factor. Now, let's say you want to please your boss, and so you push with 201 newtons of force. Will that do it? Will that break the friction? Sure. All right, so that's what you do. You push with 201 newtons of force. You're impressing your boss. He's like, wow, look at you go. So I would like you to consider if we push with 201 newtons of force, we break static friction. What kind of friction takes over? Kinetic. So now kinetic friction takes over. Kinetic, I just erased all of that. Kinetic friction is generally less than static friction. So let's say that kinetic friction in this circumstance is 0.2, that the coefficient of kinetic friction is 0.2. Erase, stupid thing. You've got to be, well, let's try that again. So you break static friction, you apply a 201 Newton force. That breaks static friction, and kinetic friction takes over. Kinetic friction, in this case, is 0.2. I'd like you to find the acceleration of the box. Right, you understand we broke static friction, and suddenly the frictional force is going to be less because mu is less. So the forces are going to be unbalanced. I'll give you a small reminder. Kinetic friction is equal to mu k times normal force. Give it a try. The answer is about 2 meters per second squared. See if you can get to the answer. It's almost the exact same thing we just did. This is a net force equals ma problem. What direction do you think the system's going to accelerate? In the x direction or the y direction? X. So I think we can skip down and say net force in the x direction equals ma. That means net force in the y direction equals 0. The box is going to accelerate to the right. That makes perfect sense. Are any of the forces here going to be in different directions than what we've already drawn? Are there any more arrows that we have to add to this, or is this the same arrows that we're going to have as before? Same as before. All right. So let's start with the top one. Net force in the x direction. What forces are acting in the x direction? Go ahead.
What? I was
Sorry. Hand went up. You have to answer now.
What was the
What forces are acting in the x direction?
The force applied and FK.
All right. So which one should I make positive?
I did forces applied.
Okay. And you made the friction negative?
Mm-hmm.
And that has to equal ma. All right. Excellent. In the y direction, what do we got? Same 2? Normal and weight. So normal minus weight equals 0. All righty. So there's an obvious substitution we made last time. We don't have to write the weight. We can write mg, can't we? So I'll just skip a step here and write normal equals mg. Is that good for you guys? All right, let's bring everything we have together. We've got this, this, and this. I only need one of those. Well, that. Now, we were told that we're applying a force of 201 newtons and that the mass of the box is 50 kilograms and the coefficient of kinetic friction is 0.2. We just got to mash this all together until we figure out what the acceleration of the box is. Now, we can put the numbers in first if you'd like, or we can just leave the letters in there. It doesn't matter to me. You guys tend to like putting the numbers in first. I would encourage you to learn to use the letters first, because there will be problems where all you have to do, that you won't have numbers, that you'll just have expressions. So I'm going to do the letters, okay? But you're looking for a pathway to get to this variable. You want that. I'm going to point out that one of the things that you could do is start realizing the stuff that's been given. All of those things have been given, right? So you have numbers to put in for all of those. So I'm just going to start substituting. For example, the first substitution that I see is putting the normal force in here. That seems like a quick substitution right away. That look good to you guys? Because now I know all 3 of these numbers. That's a good substitution to make. And looking up at that top equation, I'm noticing that if I make one more substitution, I'll have a relationship that has all stuff in it I know. So I'm talking about doing this. Do you see what I'm trying to do? All right, I'm going to write that down near the middle of the screen then. So I'll get the applied force minus mu k mg equals ma. So I just did lots of substitutions as part of my analysis that tells me that I could figure out the acceleration if I know all of those things. And I know all of those things. Like it's 201 applied forces minus a 0.2 times 50 times 10. That's the amount of friction that there is. And that has to equal 50 times A. Not terrible? So 0.2 times 50 times 10, that's 100, right? So 201 minus 100 equals 50A. Well, that just means A equals 2. Right? 101 divided by 50 is about 2, right? 2.02 or something like that, but I'll just say 2. So you break friction, keep pushing, and the box accelerates. Now, we're not going to have time to finish this next one, but I did finish it in second period. And I think our football player, he should take this with him. This is a good piece of knowledge. Okay? I'm gonna help the team out because I believe in you guys. I'd love to say that I'll believe in you and nobody else will. That's probably not going to be true. Let's say instead of pushing the box, you decide to pull the box. So you pull with that 201 newtons of force at an angle of 30 degrees. Now, we already know that the 200 newtons of force is effective at moving the box, right? We've already broken friction. But if we look at this, do you think the box is going to accelerate faster or slower if I pull upwards at an angle? You see, think about all the things that are going to happen. And I don't know the answer because there's variables in here that we have to kind of think about. Is the weight going to be any different if I pull up on the box? Does gravity change? No. Now the force I'm pulling with is now at an angle. So less of it is going forwards, right? That's going to reduce how much of the force is causing the box to accelerate sideways. But will the normal force be the same amount as it was before? If I'm pulling up on the box, doesn't that mean the normal force will have to respond by being less? And if the normal force goes down, what happens to the frictional force? It's less too, right? Because friction is proportional to the normal force. If you pull up on something, you reduce its contact with the ground. This is why if you're in the front line, you're blocking, or even if you're not in the front line, but you want to knock somebody around, the best way to do so is to be pushing upwards on them as you hit them. It reduces their contact with the ground and makes them easier to push back. It also changes their center of mass, makes it easier to throw them over. But that's why the offensive line, when they come up, the idea is to come up and take that defender and push them backwards by reducing their contact with the ground. It's a good football move, right? Yeah. What position do you play?
Receiver.
This has nothing to do with you.
I can play a little defense too.
All right. Just get out there and catch that ball. You're nice and fast? Nice and fast. Which receiver are you? Wide?
I play mostly W, so stop.
All right. All right. Now,
What number?
it's easy to pick out with the helmets. They all look the same to me too. So, you notice this problem's going to be a little harder to do, right? Not much harder, but a little harder because that force that we're applying now is going to be in both the X direction and the Y direction. But are you still able to realize that the box is still going to slide along the ground, right? So the acceleration of the box isn't going to be up or down. I don't think we're pulling hard enough on the box to lift it off the ground. The box weighs 500 newtons. Our 200 newtons isn't going to do it. But it is going to slide along the ground. But now part of our force is going to be directed sideways, and part of our applied force is going to be upwards. So although this was 201 newtons, this will be 201, bless you, sine 30, and this will be 201 cosine 30. Now the weight hasn't changed, it's still 500 newtons. But the normal force has definitely changed. And I'm pretty sure the frictional force has changed. Now I'm trying to work the problem out, and I'm trying to accelerate this so we can get to a conclusion in 1 minute. Net force in the x direction is still going to equal ma. But now we've got 201 cosine 30 minus friction equals ma. Net force in the y direction is still going to be 0. But now there's 201 sine 30 plus normal minus 500 equals 0. It's a little more complicated because we have this additional force upwards. Now your job, and I would try this weekend, is to put this together and add in a little bit of this friction stuff. Not S, K. And figure out, well, does it accelerate more or less under these conditions? You're right, we're pulling less in that direction, but there's less friction too. All right. Folks,